Hello, my name is Marcus Agun, and this is Lab 4. All right, so in this lab, we'll be exploring the oscillation of a spring using the energy principle and Newton's second law. And the goal of this lab is to create a computational model using physics concepts to model the trajectory of the weight of the weight on the string as the string moves around and oscillates around accurately. All right, so the energy principle is energy is equal to kinetic energy plus gravitational potential energy plus spring potential energy. And then the change in energy is equal to the change in all of the other energies. Gravitational potential energy near the surface of the Earth is equal to negative mg times height. Um, and kinetic energy is equal to 1/2 mass times the magnitude of velocity squared. The spring potential energy is just equal to K over 2 times the compression or stretch of the string squared. So in the tracker, we have the tracker and we look at the position of the spring over time, and that's what we're trying to model with our computational model. The relaxed length of string is 0.123 meters, and the weight on the string is 0.4402 grams, and the spring stiffness constant is 6.83 Newton meters. All right, so first we insert the initial condition, so the ball mass, right, and the initial ball's position, the initial ball's velocity, right? And then after that, um, we we figure out what G and K and L naught are, and we put all those in. And then after that, we calculate the kinetic energy, the gravitational potential energy, spring potential energy, and then E. So we just apply the concepts we learned in the energy principle. So 1/2 mass times velocity squared, and this is gravity times the ball mass times the height, which is just the ball position in the y direction. And this is just 0.5 times K times the compression slash stretch squared. In this case, the stretch. And then after that, we have to use Newton's second law to update the position and velocity. So Newton's second law, so V final is equal to V initial plus F net over N times delta T. And then that's to update the velocity. To update the position, we use the final position is equal to initial position plus V average times delta T. And we just approximate V average to be the final velocity. And then after that, we what's called update the kinetic energy, gravitational potential energy, and um the spring potential energy based on the new velocity and position of the weight. All right, the results. So these are the results. This is the change in energy between gravitational potential energy, spring energy, and then you have kinetic energy and stuff like that. So as you can see here, the total energy is equal to 0 because everything is treated as a system, right? So right here, the total energy is 0. And then when you sum these up, so like this is like negative, this is gravitational potential energy, it's the negative of the spring energy. And if you add them, they both equal 0. And then we have the position versus time. As you can see in the x position, the position versus time is really close to the computational model. In the y direction, it's not as close, but it's like close enough to be somewhat accurate. All right, and what does it all mean? So essentially, the energy principle is satisfied because in the energy versus position graph, the energy always added up to equal 0. Since there was no change in energy, it always added up to be 0 since everything was in our system. As kinetic energy or spring energy increased, the gravitational potential energy decreased. So total energy change continued to end up being 0, so it was satisfied. And in the period of oscillation, in the x direction was around 1.5, and the period of oscillation in the y direction was around like 2 seconds. So by this we can presume that choosing different directions produces different deviations in like the oscillation period. This difference is probably like due to like drag or air resistance, and also one of them goes in like more of the direction of the spring because the top it's the weight is below the attached point. So yeah. All right, thank you.